So now that we've talked about polar coordinates, what they are, some of their applications, but we really thought about it as r is a function of theta, and so it was more like a single variable calculus approach to using polar coordinates. Now we're going to convert so that we think of both r and theta. We can think of them both as variables. So, two things. First of all, previously we saw that area area is always the double integral over the region of dA. Now, in rectangular coordinates, dA was just dx dy, because you get little rectangles. So dx times dy. Now, in polar coordinates, we saw that the area was the single integral of half r squared d theta. Now we're going to turn this into a double integral, and there's a couple different ways we can do it. Okay. So one way, the way I like, is to use differentials. So in polar coordinates, we can make a tiny little sector. So how can we do that? We can think about what happens when you have a small change in r and what happens when you have a small change in theta. So when you have that, you basically have a tiny little almost rectangle. So what are the dimensions of this almost rectangle? So from your little change in r, you've got a side length of dr. And from your little change in theta, notice that the length on the graph of this side is actually going to depend on what r is. So just recall, I guess, from Traeger circle geometry, that your arc length is like, for a change in angle, is like r times theta. So in this case, your little angle change is d theta, so that the length of that side is r times d theta. So the dimensions of that are dr and rd theta. So that tells you that the area of that little dA bit is going to be rd theta. Now I'm kind of gliding past the fact that this isn't exactly a rectangle. Using other methods, we can prove that this method, that this approximation actually is exactly true. It's close enough to a rectangle for our purposes. So one way to do that is to use geometry. We can go through this whole calculation. I'll just leave it. I'll leave the calculation here, and you can look at it at your leisure. That's a bunch of geometry and quite a whole bunch of algebra. Long story short, it does give us what we need. That dA equals r drd theta. The third way is my favorite because it just uses a nice little trick. So note that half r squared is just the integral of rdr. So just make a substitution. And previously we showed the area was half r squared d theta. Well, substitute it in, you just get the double integral of rd theta. I like that one. So the take-home message from this should be that, here we go, dA equals r drd theta. So how can we find, so let's apply this to a problem. So find the area enclosed by a circle radius 2. Pretty straightforward. So the area is just going to be the double integral over the region of dA. Now we're going to do this in polar coordinates. So in polar coordinates, what do we have? So first of all, we know that dA converts, to r drd theta. Second, what are the boundaries of the region? Well, the boundaries of the region, we got to think of them in polar coordinates. So we're trying to describe a filled-in circle. So we know theta should go from 0 to 2 pi. And we know that r, we need to describe the entire two-dimensional area region. So notice that over that entire region, The smallest radius is 0, that's at the center, and the biggest radius is at the boundary, and that's 2. So we want R values to go from 0 to 2. And that's how you can set up your boundaries. And now the integral is set up, and now we can just calculate. So integral of R dr gives us half R squared, and then evaluate that as R goes from 0 to 2. And that's just going to give us 2. And now integrate 2 d theta gives us 2 theta, evaluate from 0 to 2 pi, and that gives us 4 pi, which is, of course, exactly what we would expect, because we know the area of a circle, area enclosed by a circle, is pi r squared. So note that this equivalence also tells us how to change integral between rectangular coordinates and polar coordinates. So integrating over a region some function dx dy, that's the same as written all in polar coordinates, the double integral over the region, that same function, but again expressed in polar coordinates, of r dr d theta. So let's take a look at what that might mean. So let's do this integral. Double integral over a region of x squared dx dy, where r is the top half of the filled in circle radius 1 centered at the origin. So first, in rectangular coordinates. So there's the original integral. Now how do we set this up? So the top half of the circle, it's going to make, a little more sense to make vertical slices. So the boundaries, since the radius is 1, the boundaries for x are going to be from -1 to 1. And then on each slice, the boundaries for y, starting at 0, and then up to the circle. So that's going to be y equals the square root of 1 minus x squared. Okay. So now let's go ahead and do it. So the integral of x squared dy gives us x squared times y, evaluating from y equals 0 to y equals 1 minus x squared. Okay, so plugging that in, you get integral from -1 to 1, x squared times the square root of 1 minus x squared dx. Okay, now it turns out this integral is actually possible, but the techniques are actually pretty advanced. So let's see what happens if instead of trying to do it in rectangular coordinates, we try to do this in polar coordinates. Here's what happens in polar coordinates. First step, rewrite the integral. So we know that x squared, we know that x is r cos theta. That's how we convert. Next, we know that dx dy is just dA, which means it's the same as r dr d theta. And then finally, we need to describe the region. We need to describe the boundaries of the region. So notice that this is just this piece of a circle. So for this piece of a circle, what are the boundaries on theta? We know theta goes from 0 to pi because it's the top half of the circle, and it's all completely filled in. So we know that r goes from 0 to 1. And those are the boundaries. And now we've got constant boundaries. This actually winds up becoming a pretty straightforward integral. Let's check it out. So after simplification, we get the integral from 0 to pi, integral from 0 to 1. The function becomes, combine all the r's, you get r cubed times cos squared dr d theta. So first, do the integral dr. You just get 1/4 r to the 4th with the cos squared theta sitting there. Evaluate that from r goes from 0 to 1. You just get 1/4 cos squared theta. Now I've got to integrate that d theta, and once again, we're using the double angle formula. So that becomes 1 plus cos 2 theta, and a 1/2 pops out. So the constant is 1/8. I'll put that on the outside. The integral of this is just theta plus, and then after the substitution, you get sine 2 theta over 2. And now I've got to evaluate from 0 to pi, plug it in. Plugging in 0 will just give you 0, so plugging in pi just gives you pi, but then times 1/8. So the final answer is pi over 8. So in this case, notice how much simpler it is to do with polar coordinates. And the reason for that is because the original region that we started with is so easy to describe in polar coordinates, because it's not a circle, but it's circle based. Okay. Maybe one more example here. So let me scroll down so we can see the picture just for 1 second. So find the area of the 3/4 annulus. So it's the part of the region between two circles, radii 2 and 3, in the first 3 quadrants. So there's the graph. Okay. Now imagine trying to set this integral up using rectangular coordinates. How do you slice it? Vertical slices don't make sense. You get a mess. Horizontal slices, same thing. It's really, really hard to sort of think of how do I slice this and make it work out. But this is because it's circle based, it's very easy to describe this region using polar coordinates. So using polar coordinates, we know that simply that the angle goes from 0 to 3 pi over 2, and the radius, it tells us in the question, just goes from 2 to 3. And that tells you exactly how to set up your integral. So the area of this region is just the double integral over the region dA. So now we put in the boundaries that we just said, and dA is just r dr d theta. And now do the integral. The integral, so integrating r dr, you just get 1/2 r squared. And then you evaluate r goes from 2 to 3. And you get 5/2. And then integrate that d theta, you just get 5/2 theta. Plug in the boundaries, you get 15 over 4 pi. So again, the region can be described much more easily using polar coordinates, and make the integral straightforward to do in polar coordinates. Also, it'd be possible to calculate this area just using straightforward geometry, but I wanted to demonstrate the techniques of polar coordinates.